Okay, for the last part of 6.5, really what we're going to look at is solving just more trig equations, but we're going to be using the identities to get that done. So I'm going to go through some of the identities that you might use to kind of bring out and solve some of these equations here. Now, probably one of the main ones is going to be, of course, your Pythagorean identities. And really all you're going to use is just the basic one, that sine squared plus cosine squared equals 1. And the idea of using, a lot of times, to use the identities to solve these equations is so you can have an equation that only has sine or only has cosine in it. You'll see what we kind of look at just, just a little bit at an example of that. Now, other identities that you'll kind of use a good bit are your double angle identities. Okay, so for instance, sine of 2 alpha is equal to 2 sine alpha cosine alpha. And really, you could use sort of either side of this identity. Mainly, the one that kind of got me was using this idea. If you see a sign like sine x times the cosine of x, all we have to do is just figure out how to multiply that by 2, and then we can use the double angle identity to get sine of 2x. Okay, now there again, probably not seeing exactly where this may be headed just yet. All right, some other identities you're going to be able to use here to solve these equations would be your sum and difference identities. Okay, so again, if I see, the sum and difference identities, they all have the same sort of pattern to them. The sign of alpha plus beta, or the sign of alpha minus beta, have have something to this effect. So they have sine alpha, cosine beta, and depending on if it's a sum or a difference, if it's a sum, it's plus, if it's a difference, it's minus, and then cosine alpha, sine beta. So if I see this pattern here where I have the same alpha angle and the same beta angle, then I can take advantage of that. And again, what I would actually use on the identity would not be the right side of the identity, but the left side. So this one, this side, sine of alpha plus or minus beta. And so what if I did, if I could figure out the alpha and the beta, I could actually add them together and just use that. So I can condense all of this stuff down to just one expression like that. Okay, other things that you might use, I didn't really find any ones with power reducing formulas, which is pretty good news, or product to sum or sum to product. But we're definitely going to look at using the Pythagorean identity, the double angle identity. I just wrote down the one for sine, of course. We're probably going to use the one for cosine too. Remember, cosine has 3 double angle identities, and then a sum or difference identity. Now let's take a look at the first example here. All right, so it says, and this is the nice thing about these problems, is the directions are going to give away to use an identity. Okay, so you're going to have to start looking here and thinking of the equation. What's an identity here I can use to help me solve this equation? Okay, Pythagorean identity, sum to product, product to sum, double angle, sum and difference, Pythagorean identity. What could I use here? Now, here's the thing that we've got to notice on this problem that's going to give away what to use. You have a sine squared and then a cosine x. Okay, so you want to try to stay away from having sine and cosine in the equation. And so what we mean there is we just want to have just sines or just cosines, but not both sine and cosine. So to get around it, what we can do is, since this is sine squared, okay, and not just sine, is we can use a Pythagorean identity right there. So for sine squared, recall the Pythagorean identity. For sine squared, I can say that sine squared theta would be equal to 1 minus cosine squared theta. And so notice when I put here in place of sine squared x, I'm going to put 1 minus cosine squared x. Now my equation only has cosines. Okay, so now I can go through and start trying to solve this. Now let's kind of clean it up a little bit. I'm going to combine this 1 with that -6 right there. So that's going to leave me with negative cosine squared x minus 6 cosine x, and then minus 7 equals 0. Okay, now recall, this sort of fits that quadratic-like form, and so the way we can solve this one would be by factoring. Now, so I'm going to do this. I don't really like having a negative in the front. We never like that negative when we're trying to factor something. So I'm just going to divide through or factor out a negative here. And so that's just going to make it say cosine squared x plus 6 cosine x minus 7 equals 0. So right there again, I've got this quadratic form of x squared, x, and then my constant. So I'm going to use that substitution idea and let a be equal to cosine x. And that way it'll be a lot easier to solve. So now I would get a squared plus 6a minus 7 equals 0. And so now factors of 7 that subtract to give me 6 would be 7 and 1. So let's see, they're going to be different. It's going to be plus 7 and then minus 1. So now I'm going to get a equals -7 and then a equals 1. Okay, so recall what a was here. A was the cosine of x. So now I'm going to get cosine x equals -7, and then cosine x equals 1. Okay, now in this case, when we get cosine x equals -7, well, -7 is not exactly on my unit circle. So what I could do there is just punch in, well, what's the inverse cosine of -7? Okay, now what you're going to find though, oops, kind of messed up there. What you're going to find there, if you recall, the domain for inverse cosine has to be in between -1 and 1. So because -7 is not in between -1 and 1, it's basically not going to lead me to any solution. So this part is sort of extraneous. Okay, it's not really going to give me a solution. Again, what's going to have to happen is this value has to lie in between -1 and 1. And so 1 certainly does that. And another thing is, -7 is not on your unit circle. So it's not going to work. Now, where is the cosine equal to 1? So on my unit circle, all right, I can see that my cosine is 1 at 0. Okay, so it'll be at 0 and at 2 pi, but recall here that we're not including the 2 pi part. So my answer there would just be 0. Okay, now notice the big picture in this is this idea. When I looked at it at first here, I had a sine squared and a cosine. And so my thoughts are, hey, if I can get only sines or only cosines in my problem, then I can probably solve that. And so I made a substitution there for sine squared using a Pythagorean identity, because I can write sine squared as 1 minus cosine squared. And then at that point, I only had cosines in my problem. All right, let's go to the next one now. All right, so this one says, use an identity to solve the following equation on the interval from 0 to 2 pi. Now notice again, I've got cosine on this side and sine on this side. So again, I'm mixing cosines and sines together. Now let's see if we can maybe spot an identity to use. Now notice neither of them are squared. So that kind of throws out the idea for a Pythagorean identity. Now, what you should be recognizing to use here is this part should tell you that. And so what we're really going to use is a double angle, okay, because you have cosine of 2x. Now, I'm going to use double angle formulas on the right side here, and we're going to figure out which double angle cosine would I use, because there's 3 of them. So let me jot them down real quick. Cosine of 2 alpha is equal to cosine squared alpha minus sine squared alpha. Okay, the other one, cosine 2 alpha, is equal to 2 cosine squared minus 1. And then finally, the third one, cosine of 2 alpha, is equal to 1 minus 2 sine squared alpha. Okay, so I'm going to figure out, well, which one am I going to use to put in place of cosine of 2x? Now, keep in mind, on this side, I have sine x. So I probably want to use one that only has sine in it. And so that would be this third one. That way, I can only have sines in my problem instead of sines and cosines. So I'm going to fill in for cosine of 2x that 1 minus 2 sine squared x. All right, and now we're going to have equal on the right side, sine x plus 1. Okay, now let's see how we can solve this. So notice I have a sine squared and a sine, but at least that they're both sines. Now let's figure out how we're going to solve this. Now because I have a square one and because I have a linear one, I can use that quadratic form thing again. So I'm going to use the quadratic form, which basically means I'm going to solve it by factoring. Now I'm going to put everything on the right side to set it equal to 0 and solve by factoring here. One reason I'm putting it on the right side is so that I can make that positive. So now that would be positive 2 sine squared x, and then we'll bring down plus sine x. Now we'd subtract that 1 over, and that's just going to get rid of them there. Okay, so now we can solve this by factoring here. So if you notice, we can factor out a sine x, and this would leave me with 2 sine x plus 1. Okay, now that we've got it factored, we're just going to set both factors equal to 0. We get sine x equals 0 and 2 sine x plus 1 equals 0. So now let's solve these. So my first one there, where is, on my unit circle, where is the sine? 0. Okay, so that would be at 0 and also at pi. So we have 0 and pi there. Now let's solve the other one. So my other one, I'm going to subtract the 1. So I'll get 2 sine x equals negative 1, and then divide by 2. So we'll get sine x equals negative 1/2. So let's notice, well, where is the sine negative 1/2 at on my unit circle? And so that would be at 7 pi over 6 and 11 pi over 6. So 7 pi over 6 and then 11 pi over 6 where the sine is a half. So it's got 4 solutions on this one, mainly because it was a quadratic. You know, normally quadratics have 2 solutions. So a quadratic trig equation, a lot of times, is going to have 4 solutions to it. Right, now, there again, let's spot here the identity that I had to figure out to use. The sort of 2x gave it away. And so if I kind of know my double angles, not necessarily that you have them memorized, but you know the basic idea of what they look like, then we should probably know that cosine of 2x can be written with that identity where it only uses just a single sign. And so that went back to this one right here because it only had sine squared, and this side had sine. Now my equation only had sines in them instead of having cosine and sine. Let's look at another one here. Okay, now at first when you may see this one, you may also recognize, well, this is probably another double angle problem. And so I believe that's pretty well correct here. Now we're going to use the double angle formulas again. Let me copy them real quick so I don't have to write them over. And let's see if you guys can kind of figure out which one's going to be useful for me here. Okay, so notice the reason why I can't just attack this one, I probably should have said this from the beginning, is because the argument here was different. Okay, that was cosine of 2x, and this one's just cosine of x. So we kind of can't put them together there. So, if we took out that 2, all right, we could just say cosine of x plus 9 cosine of x will be 10 cosine x. But because this one was a 2 right there, that kind of messed that up. So now, what I need here is a double angle, but I don't want one that has sine in it. Okay, so that kind of rules out this idea and rules out this idea. So I'm going to use that one because it has cosine squared in it that'll go with this cosine pretty nicely here. So now let's fill this in. For a cosine of 2x, we're going to use this double angle formula right here. So I'm going to fill in for cosine 2x, 2 cosine squared x minus 1. Now let's continue here with like the rest of the equation. Plus 9 cosine x plus 5 equals 0. Notice it's going to be one of those quadratic ones here. We have a square one and a linear term. So we may use that substitution idea here. Now let's clean it up first. The negative 1 plus the 5 would be 4. So we'll get 2 cosine squared x plus 9 cosine x plus 4 equals 0. Okay, now I'm going to solve this by factoring. And so to kind of make it easier by factoring, I'm going to use that substitution method. I'm going to let a equal cosine squared x. So now I could write this as 2a squared plus, I'm sorry, I just meant to say cosine x. So now it would be just 2a squared plus 9x plus 4. I get x from, it's supposed to be a right there, equals 0. So now let's solve it by factoring. Notice it's got a leading coefficient, so we're going to have to split this. So notice 2 times 4 there would give me 8, and factors of 8 that add to give me 9 would be 8 and 1. Okay, both signs are both going to be plus. Okay, now let's group them. So we can get out of 2a here. So we get 2a times a plus 4. We'll factor out a 1. So we have 1 times a plus 4. And so now we'll get a plus 4 times 2a plus 1 equals 0. So a here is going to be negative 4 and negative 1/2. Okay, so now let's recall what a was. We used a substitution. We said that a would be equal to cosine x. So we'll get cosine x equals negative 4 and cosine x equals negative 1/2. Now this one's not going to lead me anywhere because recall I would do the inverse cosine of both sides, and so I would end up doing inverse cosine of negative 4. So because that doesn't fall in between negative 1 and positive 1, I'm not going to get anything from that. Okay, so there again, what has to happen is this has to fall in between negative 1 and 1 there. Okay, it's got to be something there again that's going to fall on my unit circle. Okay, and certainly negative 4 does not. Now, let's look and let's see, well, where is the cosine negative 1/2 to get my solutions over here? So let's see, cosine is negative 1/2. I can't find it. Oh, there it is. Okay, cosine is negative 1/2 at 2 pi over 3. Okay, it's also negative 1/2 at 4 pi over 3. So I just got 2 solutions this time. Okay, so then go back. Notice what tipped me off here was the fact that this was 2x and this was x. I couldn't put those together. So I figured out, well, hey, that's a double angle. And there's one of those double angles that only has cosine in it, as opposed to the other two, which one had a sine, and then the other one, the first one, had cosine and sine. So notice, probably you would be using either maybe this one or this one quite frequently because, again, this one only has a cosine and this one only has a sine. So they're pretty beneficial there to help you out with solving equations there. Now, let's look at this one. Now, this one was very, very tricky to me. I couldn't really find an identity because I wasn't really looking for this and I was trying to think of a way to kind of tip you off to what to do here. But I want you to think of it, is there an identity here that has sine x cosine x? First I thought, well, maybe that's a product to sum, but that would make it more complicated if you used a product to sum there. Okay, well, I guess I'll just have to give it away. It's a double angle. Okay, and the thing is, you're probably not thinking double angle because you don't see like the 2x. But what it is, it's just the right side of the identity that you're using. Here's the identity that we're going to use. Sine 2x, or let me use sine 2 alpha, is equal to 2 sine alpha cosine alpha. Okay? The key is to spot this. If I see a sine x, or whatever the variable is, sine x times cosine x, then that's a good hint to use a double angle. Okay. Now, the problem that you're going to spot is, well, Tatum, we don't got a 2 right there. Well, we can easily make a 2 right there. And so how could I do a 2? Well, I could multiply both sides by 2. So if I did that, multiply this side by 2. So if I do multiply this side by 2, that just means I have to multiply this side by 2. So now I get 2 sine x cosine x. And notice I'm not going to distribute 2 because it's not adding and subtracting right there. Equals, now 1/4 times 2, that would just be 2, I believe. No, I'm sorry, 1/2. 2 would go into 4 2 times. So that would just be a half. And now I got my 2 there. So 2 sine x cosine x is sine 2x. And so now I'm just down to a sine and not sine and cosine. Now notice on this one, it's going to be a little bit tougher because we've got that nasty old coefficient. So that means we've got to go and do our plus 2 pi n thing. Okay, so let's get started on this part. All right, we're going to let 2x equal theta here. So we've got now cosine theta, or sine theta, equals 1/2. So let's think, where is the sine 1/2? So sine would be 1/2 at pi over 3. And let's see where else. I can't think about it. Let's see. And at 5 pi over 6. Oh, I think I said that wrong. That's not pi over 3. Sine would be 1/2 at pi over 6. Okay. And 5 pi over 6. Now, because we had this coefficient, because we had to use that double angle, I'm going to have to find all my solutions. So I need to say my general solution here plus 2 pi n. Right, so now recall here that theta was equal to 2x. So now we're going to get 2x equals pi over 6 plus 2 pi n. And same thing here, 2x is equal to 5 pi over 6 plus 2 pi n. Okay, now we've got to get rid of the 2. So we're going to get x equals pi over 6 divided by 2 would be pi over 12. So we get pi over 12 plus, now the 2's would cancel there. So it would be plus pi n. Let's see this one divided by 2. So here we're going to get, this is going to give me 5 pi over 12 plus pi n. Okay, so now, there again, since we got the coefficient, we have to do all this it's not unnecessary, but we have to do all this stuff that we don't like to do, okay? And so n cannot equal -1, that's going to make it negative. So let's start off with n equals 0 here. Okay, so if n is equal to 0, we're going to get a solution of pi over 12 and 5 pi over 12. Okay, now let's see what we can get for n equals 1. So for n equal 1, we get x to be pi over 12. Now if n is 1 right there, pi times 1 would just be pi. So we get pi over 12 plus pi. So I'm going to think of that as pi over 12 plus 12 pi over 12, which is going to give me 13 pi over 12. And certainly that's okay. That is less than 2 pi. Now, Let's do the other one here. Again, we're going to let n equal 1. So we're going to get 5 pi over 12. Let me rewrite that. 5 pi over 12 plus pi. And so that's like saying here, well, pi over 12, excuse me, 5 pi over 12 plus 12 pi over 12 would be 17 pi over 12. Now, if n is equal to 2, notice this is going to be 2 pi, and pi over 12 plus 2 pi is going to be bigger than 2 pi. And so same thing happens with the other one. So 0 and 1s for n is going to work. So now let's circle all our solutions. So we got pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. Okay, so that's 3 in a row that we've done with the double angle. Now, I'm going to caution you, a lot of these problems are going to be sort of distracting with the double angle. And it's because you see a 2x doesn't mean that you're going to use a double angle. But certainly when you see a sine x times a cosine x, that's a prime double angle problem. And what you really have to recognize is, we realize this is double angle. But when we see this part, it doesn't really hit us as much. And we really sort of need to learn that. And so that's why it's kind of helpful to know your double angles when you see them. And not just the left side of the identity, but the right sides of the identities too. Now, before we talk about that one, I'm going to kind of insert a little slide here. And it's just going to bring us something back, an old algebra thing. Okay, so if I have, for instance, an equation that would probably be false, like this one, x squared equals -5. I'm sorry, I meant to say square root of x. Got that backwards. So if you notice, that would be false because I could not take the square root of something and get a negative result. Now, just stick with me on this. Now, if I was trying to solve this, it's no solution because it's not true. But if I were to solve it, I would undo the square root by squaring both sides. And so we would just get x equals 25. But notice that's not going to be true. If I take 25 and put it back in right there, the square root of 25 is 5 and not -5. Okay, my point is this. Okay, when you square both sides, and we could expand this to not just when you square, but when you raise both sides to an even power. Okay, but it's also working when you're going to square both sides, which is what you're going to do. And when you square both sides, you must check for extraneous solutions. And this equation right there tells you why. Because really and truly, this equation would not have a solution because the square root of something can't equal something that's negative. But yet when I square both sides, it seems to work out. So this is why we have to check here. So if I square both sides of an equation, I have to check for extraneous solutions. Now it kind of gives away the strategy that we're going to use on the next one here. But let's kind of look at why would we square both sides. Now, one thing I'm going to do on this one to make it just easier on me here is get rid of all of these little nines. Okay, so I think all the equations are really just going to wind up being the same thing, which is going to be this. Okay, so you're probably going to get sine t plus cosine t equals -1, or the variation that you might get right there would be a +1. Now, notice the plus sign in between. That kind of creates a problem because, see, they're different. And notice neither of them are squared, so I couldn't use a Pythagorean identity. Now, I can't use a double angle because, recall, the double angle would look like this. It would be sine t times cosine t. And if that was the case, I'd multiply both sides by 2 and get my double angle working there. Okay, but there again, in the double angle, it's times, it's not plus. So that doesn't work. So what I really need here is I need one of these to be squared for me. Okay, and let me put a star beside that because this is by far the toughest equation here. Doesn't really look all that bad, but trust me here, it certainly is kind of hard to do. So here's the big idea. We need a square. And so let's think, how could we get a square? Well, could we just square both sides? And if I square both sides, then I can get some squares going. Okay, so that's the approach here that I'm going to take. I'm going to square both sides. Now, because I'm doing this, I'm going to have to check my solutions. You're going to get some solutions, and you pretty much guarantee that some of them are going to be extraneous. Now, let's square both sides. -1 squared will be 1. Now, when I squared sine t plus cosine t, and this is what I'm going to say, square, square, twice the product. So this would be sine squared t plus, now, twice the product would be 2 sine t cosine t, and then plus cosine squared t. Okay, now, once we square both sides, you should recognize there's two identities. Now, you probably spot one for sure, but the other one you're probably not going to spot. I'm going to help you with it. Now, we should spot that sine squared plus cosine squared would give me a 1. Now, I'm still left with this in the middle right there, and this is where we need to recognize we just used this not too long ago. Okay, remember this problem? When we see a sine x, cosine x, this is going to be a double angle. Okay, so let me show you back here. So this would be the double angle formula for sine. Okay, so watch here. We're going to say sine squared and cosine squared is going to give me 1. And then this right here, this is my double angle for sine. Okay, so this would be sine of 2t. Okay, which brings in the coefficient, which we don't like. Okay, now, but notice we use a Pythagorean identity and a double angle identity. What led me to all this was thinking, hey, I've got to get some squares going so I can do something. Okay, so anytime you have like a sine plus a cosine, or even a sine minus a cosine, okay, and then they're not squares, either of them aren't squares here, you're going to have to square both sides. So, and that's going to lead to some extraneous solutions. Now, let's solve it from here. Notice the ones are just going to go away, which is pretty good there. So I'm just going to get sine of 2t equals 0. Now, I got that coefficient, little nasty coefficient, so this is going to take a lot longer. So let's see, let's let theta equal 2t. So now we're going to get sine of theta equals 0. So let's look, where is the sine of theta equal to 0? And that would be at 0 and pi. So we're going to let our theta is going to equal 0 and pi. Now, again, because we got that nasty coefficient, we're going to have to say plus 2 pi n. Okay, now recall theta was equal to 2t, so we're going to get 2t equals 0 plus 2 pi n, and 2t equals pi plus 2 pi n. Okay, now let's get rid of those 2's. So we're going to divide through by the 2. So we'll get t equals, that'll give me 0 plus 2's would cancel. So this would be 0 plus pi n, which is just pi n. Okay, let's solve the other one. We're going to divide by 2 here. So now that's going to give me pi over 2. 2's will cancel, plus pi n. Okay, so now got my two solutions. I'm going to bump this one down so it's even with that one. Now, let's see, can n be -1? Well, no, that's going to make them both negative. So let's let n be 0. Again, I'm doing this because of nasty 2 there. All right, so if n is 0, pi times 0 would just be 0. So we get t to be 0. And if n is 0 here, then that's just going to give me pi over 2. Okay, now I think we can work another one here. We could probably do n equals 1. So if we let n equal 1 right there, 0 plus pi would just be pi. So we get t to equal pi. And here if we let n equal 1, we would get pi over 2 plus pi. And so I'm going to think of pi as 2 pi over 2. So this would be 3 pi over 2. And those are both still less than 2 pi. So now, if we get up to n being 2, though, this is going to be 2 pi, which is too big. And this is going to be more than 2 pi because it's adding pi over 2 to it. So just n and 0, n to be 0 and n to be 1 is all we need. So we got t equals 0, t equals pi over 2, t equals pi, and then t equals 3 pi over 2. So those are my solutions. Maybe. Recall something. Okay? Look what we did back here. We squared both sides. So that means I have to check all these solutions to make sure that they work. This problem sucks. Okay? So let's see. Let me copy the equation. And I'm going to copy the solutions over so we can check them. There's the equation. All right, let me go back and get the solutions. So let's see. T equals 0, pi over 2, pi, and 3 pi over 2. Okay, so we're going to check all these solutions here. Okay, so let's start with 0. Okay, so let's plug in 0. So all we're going to do is plug this in and make sure this is going to be right. So we get 9 times the sine of 0 plus 9 times the cosine of 0 should be equal to negative 9. Well, let's see. Okay, so let's look on our unit circle. What's the sine of 0? Well, that would just be 0. So we're going to get 9 times 0, which is just going to be 0. Now, plus 9 times the cosine of 0. So let's find, well, what's the cosine of 0? Cosine of 0 would be 1. So we'll get 9 times 1 there. Okay, and this is supposed to equal negative 9. Now, let's see, 9 times 0 would be 0. And then 0 plus 9 equals negative 9. Well, not today. Okay, that's not going to work out. So 0 is an extraneous solution. Okay, now let's try the next one. Let's try pi over 2. So let's take pi over 2 and put it in, and let's see if it'll work. Okay, so let's see, the sine of pi over 2 is 1, so this will give me 9 times 1 plus 9, now, times the cosine of pi over 2. The cosine of pi over 2 is 0. I don't think this one's going to work either. Okay, so we get 9 plus 0 equals negative 9, and that's not true either. Okay, so pi over 2, you're a bad solution. Okay, you got to do something else. You're wrong. Now, let's check the other ones. I bet the other two are probably going to work. Okay, you're probably seeing a little pattern developing what's working here and what's not. It has to do with one of these being negative. Now, let's try pi. Now, let's put in pi, and let's see if this is true. Okay, so let's see. 9 times, all right, the sine of pi, off my unit circle here, the sine of pi is 0. And then 9 times the cosine of pi. Now, this is where we get our negative. This is negative 1, and this is going to work. This is going to be 0, and then 9 times negative 1 would be negative 9, and 0 minus 9 is negative 9. So pi is working out. So I think 3 pi over 2 is also going to work out. Let's check it and see here. So now let's put in 3 pi over 2. Okay, so let's see. What's the sign of 3 pi over 2? So that's negative 1. So we're at 9 times negative 1 plus 9 times. Now, the cosine of 3 pi over 2 is 0. So I think this is going to work. We're going to get negative 9 plus 0 equals negative 9, so that's true. So 3 pi over 2, he's a good guy, he works. So out of the 4 solutions here, only 2 of them worked. And that's usually what you get. When you square both sides, it's going to eliminate usually half of your solutions that you get. So go back. When I squared both sides in this step, that means I was going to have to check for extraneous solutions. Okay, now we have one more, and now the last one's not going to involve any sort of identity. Oh, I'm sorry. That was not the last one. All right, using identities. I got to use an identity somehow. Now, this one was also fairly difficult to sort of realize, well, what identity am I supposed to use? Now, what's distracting is my first instinct, double angle. But if you put your double angle formulas in there, they don't really make it any easier. They actually make the equation harder. Okay, so you have to look somewhere else besides a double angle here. Now, the key is to notice this 2x and this 2x, they're both 2x's. Now, I know one of them's sine and one of them's cosine, okay? And then on this one's x and this one's x. So we'll see if you can spot it here. We'll give you a second to think. What identity is this? Maybe we can use to make this a lot easier on us. So here's another hint. Get my formula sheet. How about this one's alpha and this one's beta? Notice that the alphas are both 2x and then the betas are both x's. This is a sum identity. This is the sum or sine of alpha plus beta. Okay, so that's really, really hard to spot on this problem. But there again, that's where it's good to really know your identities instead of just kind of glancing at them at the reference sheet and using them when I'm supposed to. You also have to recognize them. So recall that this is sine alpha times cosine beta plus cosine alpha times sine beta. And so what we have here is that the alpha is the 2x, see, sine alpha, cosine alpha, and that the x is the beta. Let me do that for color so you guys can really see that. See, that's the x, there's the x, so the x is going to be the beta. So now, what's kind of tricky on this one is I'm not really using this side of the identity. What I'm really going to use is this side. Okay, so the alpha is the 2x, the beta is the x. So now I could write this as the sine of 2x plus x equals negative 1/2. Okay, and now I can see that sine of 2x plus x would just be sine of 3x. So it's kind of like using the identity backwards from what we're used to there. Okay, now notice, got a little nasty coefficient there, so I got to do my whole thing where I got to do my pi plus 2n. Crap, I didn't mean to do that. Undo button. Let me slide this over a little bit. Now, so I'm going to let theta here equal 3x, and we'll solve our easier equations. We have sine of theta equals negative 1/2. So let's look on our unit circle. Where is the sine? Negative 1/2. And so that would be at 7 pi over 6. And then at 11 pi over 6. Okay, now we're going to have to add our plus 2 pi k, so I'll kind of bring them out so I can give myself some more room here. So we'll have to say plus 2 pi n. Okay, now recall theta was equal to 3x. We'll get 3x equals 7 pi over 6 plus 2 pi n, and 3x equals 11 pi over 6 plus 2 pi n. Now, let's get rid of these 3's. So divide by 3. So now we'll get x equals, all right, 7 pi over 6 divided by 3 would just be 7 pi over 18 plus 2 pi over 3 n. And now for my other one here, we'll divide it by 3. So we'll get x to be, this will give me now 11 pi over 18 plus 2 pi over 3 n. Okay, now let's let n equal some things here. Now, let's maybe try -1. Okay, now if I got -1, notice that, what may help you out here is if you wrote that in the form of something over 18. Okay, so I might redo that. So 2 pi over 3 in the form of something over 18 would be 12 pi over 18. So notice if I let n equal -1, I would subtract that, and then that would be negative. Okay, so -1. Haven't seen any that work with -1 yet, so I think we can pretty much disregard it now. So n equals 0. Let's put 0 in. And so that would just give me 7 pi over 18 for that one. And if n equals 0 there, that would just give me 11 pi over 18. Okay, now let's see if n equals 1. Let's see if this will work out. So this will be 7 pi over 18 plus 2 pi over 3. Let's see if this is going to be too big. Thinking it probably is, but not positive. I need a common denominator. Now, of course, you can just punch in 7/18 plus 2/3. All right, and this would be, like we said earlier, 12 pi over 18. So now we're going to get 19 pi over 18, which is not too big because 19 over 18 is less than 2, so that one's okay. Now, let's try the other one here. So let's let n there equal pi, or equal 1. Okay, so this would be plus 2 pi over 3. Right there again, I need a common denominator. We get 11 pi over 18 plus, and then write that as 12 pi over 18. So 11 pi over 18 and 12 pi over 18 would be 23 pi over 18, which is still less than 2 pi. Now, I think n equal 2 is probably going to be too big. Okay, but let me put it in just to see. So we're going to say 7 pi over 18. Now let's put n equals 2 right here. So if I put 2 in right there, that will give me 4 pi over 3. So plus 4 pi over 3. Okay, now we can just punch in 7/18 plus 4/3. All right, but that will be hard-headed and do it out like this. So let's see, that would be, let's see, 3 times 6 is 18, 6 times 4 is 24. And so now we're going to get 31 pi over 18, which is still less than 2. I thought it wasn't going to work, but n equals 2 works. I got a lot of solutions on this one. All right, let's do the other one. I bet the other one's probably not going to be too big either. So now let's do 11 pi over 18 plus, now there again, we're letting n equal 2. So if I put in 2 back there, that's going to be plus 4 pi over 3. Okay, common denominator again is going to be 18. So let's let's see, 3 times 6, that would be 24 pi over 18. And then 11 would be 35 pi over 18. Okay. Now notice that's just under 2, because 36 divided by 18 would be 2. So 35 over 18 would be less than 2. Now notice anything that's going to get bigger than that is going to be too big. So I'm going to stop right there. Now you could let n equal 3, but you're going to get way too big there. So we circle all 1,500 of these answers here. All right, so we got 35 pi over 18, 31 pi over 18, 23 pi over 18. All right, let's see what else. 19 pi over 18. And we had n equals 0. So it's 6 solutions on this one. Now, I'll have to check them. I didn't square both sides. Okay. I don't think I did anyway. No, I didn't. Okay. What really made you a lot of solutions there is coming up. The bigger those numbers get on the coefficients, the more solutions they get. Of course, the smaller the number, the less the solutions you get. Okay, but you got 6 solutions there that worked out for that one. Okay. Now go back again. What really scares me on this problem is our ability to spot that is a sum. Okay, so that was the sum for sine of alpha plus beta. And there again, what's going to kind of key me into it is that these two values are the same and these two values being the same, even though they were different sines and cosines. Okay, now the last one, finally, we're not going to use really so much of an identity, but it's more of a calculated problem. I'll bring up my calculator here. Now, since it says it has to be on the interval from 0 to 2 pi, what we're assuming is that it needs to be in radians. So let me put my calculator in radians. It's already in radians. Never mind. All right. So now, notice this one. You got tangent of x equals negative 3.3196. Okay. Now, I don't know about you, but I really don't know where the tangent is equal to this number. And so that's why it's definitely a calculator problem. So the way that we're going to solve this and get one of the solutions is going to be very simple, but the other one you're really going to have to use your head and think about. Okay, tangent of x equals negative 3.3196. So since I don't know where the tangent is equal to negative 3.3196, I'm going to have to use inverse tangent on both sides. So if I take inverse tangent on both sides, that tangent is going to go away, and it's going to leave me with this. The inverse tangent of negative 3.3, oh, I copied that wrong, 3196. Okay, so I'm going to punch in my calculator. We'll do inverse tangent of negative 3.3196. Okay, so I'll get a solution here of negative 1.2. I didn't see what to round it to. I guess I didn't copy that part. I'll just round it to 2 decimal places. Not really sure what we were supposed to round to. Now, got a problem with that answer here. And so my answer is supposed to fall in between 0 and 2 pi. Okay, so that's really not going to be one of my solutions that fall in between. Now, all I have to do with a tangent equation like this is remember that tangent is a periodic function here, and then the period for tangent is pi. So all I have to do with tangent is just add pi multiple times. Now, let me show you really the way that you should think about this. I mean, you could just say plus pi and then plus pi again, and it's going to give you 2 answers. But I want to show you this visually too. Okay, so let's look on a unit circle. And the way I need to think about my unit circle here is in terms of decimals, since I'm dealing with decimals. So recall, this is pi at 3.14. Okay, half of that would be 1.57. This value down here ends up being 3 pi over 2, but it's going to be 4.71, and then 2 pi is 6.28. Okay, now let's see, well, where would negative 1.28 be? Well, since it's negative, I'm going to have to go this direction. Okay, so in this terms, if I went negative, this would be negative 1.57. So you kind of tell that negative 1.28 would be in the fourth quadrant. Okay, so I'm going to draw it down here. This is negative 1.28. So the real way I have to find the solutions here is to find the reference angles. So I need to find out, well, what would this reference angle be and located in another quadrant here. Okay, so let's see if we can figure out, well, what's the actual value of that angle? Well, if that's negative 1.28 units down here, let's just find the positive version of that. And so the positive version, I could just think about going around this way. And that's going to be my positive version. So what I can do is just 6.28, which is really 2 pi, and then subtract 1.28 to find the positive version. So I'm not really going to punch in 6.28 minus 1.28. What I'm really going to do is say 2 pi because that's exact. So we'll say 2 pi, and then when we say minus 1.28, I can just hit, all right, plus and then answer. Notice I'm not saying minus because it's got the negative on it. And so this angle in terms of a positive, when you think about that, anytime we want to find another coterminal angle, we'd stay at 2 pi. So the positive form of that angle now is about 5.00. Okay, so there again, they're equivalent because they're in their same spot. They're coterminal angles. But that one lies in between 0 to 2 pi. Now, here's the thing. It's going to have another answer. Okay, most of these are going to have two answers. Now, this is where tangent was negative. So you have to think to yourself, okay, where else is my tangent going to be negative? So tangent is negative, of course, in the fourth quadrant, but tangent is also negative over here in the second quadrant. Let me do that with a different line here. Okay, so I'm going to also have a reference angle over here of that 1.28. Okay, so let's think, how could we find here the degree of the angle? Now, not the reference angle, but from standard position, how could we find that? Well, we could just say 3.14 minus 1.28. Now, we need to be exact. So what we really need to say is pi, my calculator, minus. Now, what you would have had to done here was to store that value. Okay, we're going to say pi minus. Now, I'm pretty clever on my mind here. Really, if we're just going to say minus a negative there, we really should just say plus. And I can copy this number down. Of course, you would have to store it on your little scientific calculator. Okay, so that's actually going to give me the angle of about 1.86. Okay, so we got 1.86 and 5.00. Now, kind of had to show you that because you may encounter ones where you have to draw it on the unit circle to figure them out. Now, here's the bottom line with tangent. Okay, go back. You had this one, and that was negative, so you couldn't have it. So all you have to do to your tangent answers is just add pi, okay? Or in this case, you would add pi and add 2 pi to the answer. And that gets both of them for you. Okay. The other case is if it's actually a positive number, you would have to possibly subtract pi to get the second answer. Okay, I know that was kind of long and drawn out. You may not have followed everything there, but you know you're going to have the same sort of question. So it's going to give you a tangent angle down there in the fourth quadrant. And so really all that you're going to have to do, you're going to have to take the inverse tangent. And you're going to have to take this value here. I'm sorry, I was saying this earlier. That was the inverse tangent. So what we're doing here is we're just taking negative 1.28 and you're adding pi, and then you're adding 2 pi to get those other two answers. Just think about that. Okay, let me kind of show you this another way. If you didn't follow what I was just doing there. So there again, if I'm down there at negative 1.28, I'm in the fourth quadrant. Recall the period for tangent is just pi. So if I want to get to this angle, but I want it to be positive angle, all I have to do is take it and add 2 pi. And then recall that the period is pi, and so pi is just halfway around the circle. So all I have to do is just get over here where tangent is negative. So I would just have to take that. This one would be negative 1.28 plus pi. And that's how we can arrive at that second answer there. And I believe that's it. Okay, you should be able to finish all of them. Now, you can certainly wait until Wednesday to work on the ones with the identities and the last one. Now, the other ones you should be able to finish. So only the ones with the identities and the very last question, you can wait until Wednesday. The other ones you do need to finish.